Hi, class. In this lesson, we're going to discuss correlation and linear regression. Previously, we've learned how to describe data and to display information in graphical form. And we've mostly been focusing on describing one variable. In this lesson, we're going to talk about the relationship between two variables. We're going to learn how to describe the relationship between two variables and how to graph them, how to graph the relationship between two variables, and how to use one variable to make predictions about another variable. That's what we're going to use the linear regression for. Let's start out here. Just kind of check out the Canvas site. All of your assigned readings are located in Canvas. We're going to cover chapters 8 and 9 in the textbook. I'm also going to briefly go over the PowerPoint that we have linked on Canvas. And then I also have another document here that describes some other correlation coefficients. The textbook really only covers Pearson's R and briefly touches on Spearman's Rho, but I wanted to just introduce you to some of these other types of correlations. And you can see in this little matrix here, they're really driven by the measurement scale of your variables. If you have two interval ratio variables, Pearson's R is appropriate. When your variables are both ordinal, Spearman's Rho would be appropriate. So you can just kind of use this matrix here to see what is an appropriate correlation for the type of data that you have. I'm not going to read through this, but it's kind of just kind of give you an overview of the different types of correlations that are out there. We're going to mainly discuss Pearson's R, and the textbook covers a little bit about Spearman's Rho. Let's see. Let's see. There's also in the assigned readings, I have a lot of additional internet resources. If you find the Kranzler text confusing, I've just linked to some other, what I thought were just easy to understand resources online. A lot of the material repeats itself, so I don't feel like you have to read it all. It's just kind of there for your help. There's the other correlation coefficients notes, some more little internet site on, little example of using bivariate data. Also have an example that's like the data analysis assignment. So you can kind of see I've gone through there and kind of answered it like you would your data analysis assignment. For the practice assignment, I didn't give you the data set. You're going to have to enter these data into SPSS. So you can kind of practice. It gives you some practice entering data into SPSS, and you can answer the questions and see if you get the same type of scatter plot and come to the same correlations that I did. And we'll talk about that a little bit more. Here's just a link to some of the extra internet resources. And all of those are linked in here that you can find. As always, I try to provide SPSS guides for you, and we'll go through those and kind of run through an example in SPSS together. I've also linked for a couple of videos here that you might find helpful. If you find other videos that you find are helpful, send them my way and I'll post them online for everybody. And then, as always, your assignment and quizzes are linked down here at the end of the module. Let's see. Let me pull up the PowerPoint. All right, if you notice, if you view the PowerPoint in actual PowerPoint, some of the slides will have notes here. And then, kind of give you a little bit of extra information. And then also there are a few like quizzes to test your knowledge, like here, and you'll see the answers down there, so you can check that out. But we'll sort of talk about, kind of run through this together quickly. So what is bivariate data? So bivariate data really refers to data for two variables. We have the heights of men and women, or the ages of married couples. We want to discern what's the relationship between the heights of men and women, or the relationship between, say, height and weight. And we would use, a bivariate data analysis to examine the relationships between two variables. So probably the most common measure used to examine the relationship between variables, is the Pearson's correlation, or it's called the Pearson's product moment correlation. And so this examines the linear relationship between two variables. And these are typically variables measured on an interval ratio scale. So this is the most common type of correlation coefficient. It's typically symbolized with the letter R. You may also hear it called the zero order correlation coefficient. This is all referring to Pearson's R. Some properties of the correlation coefficient. The correlation ranges from -1 to 1. The sign in front of the correlation indicates the direction of the relationship. So a positive sign means that the relationships are going in the same direction. So as we increase on X, we increase on Y. It can also mean that as we decrease on X, we decrease in Y. As long as they're going in the same direction, it's a positive correlation. The negative sign means that the relationship goes in the opposite direction. As we increase on X, we decrease on Y. So the positive and negative sign, the sign of the correlation just indicates the direction of the relationship. Are the variables moving in the same direction or opposite directions? The number indicates the magnitude of the relationship. The closer the relationship is to 1 or -1, the stronger the relationship is. The closer the correlation is to 0, means the weaker the relationship is. So just a few properties of the correlation coefficient. So I keep moving this thing so it's not in the way. We already talked about that, didn't we? Yeah, so a correlation of 1 or -1 would indicate a perfect relationship. A correlation of 0 would indicate no relationship. And we kind of already talked about this. The larger the value, the stronger the association. So we would typically, when we graph these data, we typically graph them in what's called a scatter plot. I believe he calls it a scatter diagram in the text. So a scatter plot is, just go to the next page here, you'll see we have an x-axis, which is the horizontal axis, and a y-axis, which is the vertical axis. And you just plot, okay, husband's age is 32, wife's age is 32. And so you just plot each point for each variable that you have. We'll usually plot our dependent variable on the y-axis, or the vertical axis. You also hear it called as a response variable. But we usually reserve the y-axis for our dependent variable, and our x-axis is for our independent variable. So, scatter plots are really useful for looking at the relationship between two variables. It gives you a graphical representation of that relationship. It's also a good way to determine if there's any outliers in your data. So if we look at this, what type of relationship do we see here? It looks like here, as husband's ages increase, so does wife's age. So that would indicate a positive relationship between husband's age and wife's age. So if we look at this, a scatter plot between agreeableness and behavioral problems. And it looks like that as agreeableness increases, behavior problems decrease. So this would be an example of a negative relationship. Notice they're going in the opposite direction. What about this scatter plot? What do you notice? It really seems like it's a random scattering of points. We might say that there's no linear relationship here. So the correlation would be pretty close to 0 in this instance. What about here? What type of relationship would this be? This is what we would call like a curvilinear relationship. We could probably fit a straight line through here, and it would probably be a positive correlation, but it would probably be better described as another type of relationship. We probably use a different function instead of a straight line to describe that relationship. So that's what we would call a curvilinear relationship. There's two websites here that are really cool websites on guessing the correlation. See if you can guess what the correlation might be from the scatter plots. They're just fun to test yourself on. There's a couple funny comics on, correlation does not equal causation. A new study found that Colorado has the lowest obesity levels in any state. You know what that means. We need to move to Colorado. It's not that Colorado's causing the decrease in obesity rates. It's other things that are going on there that are probably causing obesity rates to be low, not just moving there. So you probably all heard the saying before that correlation does not imply causation. And we're going to talk about establishing causation in a later module. The reason why we say correlation doesn't cause causation is because of these spurious relationships or spurious correlations. This is what happens when a relationship is wrongly inferred between two variables. And it's really because that the relationship that the correlation is showing is really due to the influence of some other variables. So, a really easy example is, ice cream sales and crime rate tend to have a positive correlation. But this doesn't mean that ice cream sales, higher ice cream sales causes higher crime rates. It's really, the effect of a third variable that's influencing both of these relationships. And that third variable would be the weather, right? As weather increases, as it gets hotter, ice cream sales increase. As it gets warmer, crime tends to increase as well. So both of these have the correlation between ice cream sales and crime rate would be a spurious relationship explained by the temperature or weather. So some factors affecting the magnitude of the correlation. So remember, the Pearson's R really examines the linear relationship between two variables. If, the actual relationship is curvilinear or has a monotonic relationship, Pearson's R will tend to underestimate the relationship between the two groups. The homogeneity of the group, as groups become less variable, the value of the correlation tends to become smaller. And we'll show an example of this in a little bit. The correlation is also very sensitive to outlying observations, and we'll show an example of this in a minute too. But generally, the size of the group doesn't affect the size of the correlation. So here's our outlier example. Notice in the graph on the left, the correlation is about 0.4, because if we look at, this is what we call our regression line, or it's really like our measure of central tendency. Notice that it gets pulled in the direction of the outlier. So the outlier tends to influence the size of the correlation. If we remove that correlation, you see all the points tend to scatter along this line. We get a stronger correlation. So what about this? Let's say that grades are correlated with IQ in an honors math class and also in a regular math class. which do you think would have the higher correlation? The answer might surprise you that it's actually the regular math class. And this goes back to the idea of the homogeneity of the group as the as the group, students in the honors class are more similar to one another. That also tend to have higher IQs and higher grades, where students in the regular math class would be more variable. If you don't believe me, we can check out like a little scatter plot of the relationship here. Notice in the honors class, they all tend to have pretty high IQs and really high grades. They're all clustering kind of together. It reduces the variability in the group, so it reduces the correlation. But in the regular math class, we have people with average IQs, people with really high IQs, people with low grades, people with high grades. We have more variability in this group, so the correlation tends to be higher in that group. Here are just some general rules of thumb for interpreting a correlation, and this is the citation from where I got it. It's from one of Hinkle's textbooks, Applied Statistics for the Behavioral Sciences. But you really need to be careful in interpreting the correlation. You really have to know the literature on your subject to determine, the substantive value of a correlation. A correlation of 0.3 may be considered small in some fields, but it may be considered substantial in some as well. But these are just general kind of rules of thumb for interpreting a correlation. So just some requirements for using Pearson's R. If we want to make inferences back to a larger population, we need to randomly sample people from that population. We want our traits being measured, our X and Y variable to be approximately normally distributed. We need the scores to be measured at least on an interval scale. We want similar variability in X and Y. When I say that the normality and homoscedasticity are robust, that just means that unless we're severely violating these assumptions, that it's not a big problem. We tend to not worry about them. And the main thing is that they are linearly related to one another. So if you square the correlation coefficient, it becomes what's called the coefficient of determination. And so it gives you the proportion of variance in Y in your outcome that can be explained by your independent variable, or X. So it's the proportion of total variance in Y that's associated with your variability in X. So it's the proportion, you can kind of think of it as how much variability do X and Y have in common. If the R squared is 50%, then it's saying that our knowledge of X can explain 50% of the variability in Y. There's still another 50% of the variability in Y that's unaccounted for by X. So, the R squared, just squaring the correlation coefficient, is called the coefficient of determination. And it tells you the proportion of variance that's associated or can be explained by our knowledge of our independent variable, or it's a portion of variance in our outcome that is explained by our independent variable. Here's a couple little practice, would these be positive or negative relationships? You can kind of read through those and look at the notes and decide. There's also a little practice quiz here, true or false. Like this one, is it possible for variables to have a correlation of 0 but still have a strong association? It's actually true. So if you look at this is a curvilinear relationship. So these two variables, X and Y, have a strong relationship. We start increasing on X, as we increase on X, we're increasing on Y up until a point. and then we start decrease as we increase and as we start decreasing in y. The Pearson correlation between these two variables would be 0, but that doesn't mean the Pearson's correlation is saying that there's no linear relationship, not that there's no association at all. These clearly have some type of association. This would be a quadratic association. But, you can kind of practice yourself going through the practice quiz. Here's the little matrix of other correlation coefficients. You can read the little handout on Canvas for more information about these different types of correlations. So linear regression. So linear regression basically is just trying to model the relationship between two variables by fitting a straight line between 2 points. We can think of this as sort of the measure of central tendency. What one line best summarizes the relationship between these two variables. If you remember, y equals mx plus b from like 8th grade algebra, that's basically what we're doing here. We're trying to fit a straight line through a set of points. The type of regression we're going to talk about is called ordinary least squares regression, because it uses the method of least squares to obtain the regression line. So regression is mainly used for two purposes: prediction and explanation. We're going to mainly talk about using regression for prediction. If we, our knowledge of X, what can we predict your Y or outcome score would be. So, can we predict end of term GPA, using your high school GPA or using your ACT score? The goal here is to develop the most parsimonious equation to predict what the outcome that we want. Most often in academic research, is we use regression to explain the relationship between variables. We want to examine what factors are influence, say, students' critical thinking, or what factors are related to some outcome, and regression analysis also tells us that. In this class, we're only going to look at simple linear regression or bivariate regression, where we only have one independent variable. Lots of times in regression analysis, you'd put more than one independent variable in the analysis. But in this course, we're going to start simply with just one independent variable. So we're going to use the concept of a correlation in a straight line to develop our linear regression equation. And so all of these regression equations are expressed as follows. The predicted y would equal sum b, which would be our slope of the line. Whoops. So this is called our regression coefficient times our x value, or the value at our independent variable, plus some constant. This A is called your regression constant, or y-intercept. It's basically the value of y when x equals 0, is what it tells you. So y would be our predicted score. B is the slope of the line. Remember, rise over run from 8th grade math. So this is the slope of the line. And it's also known as our regression constant. It's related to the correlation. And A is the y-intercept, so it's where the line would cross the y-axis. It's also called our regression constant, or it is the value of y when x is 0. So for an example, a local tennis club charges a fee of $5 per hour plus an annual membership fee of $25. With this information, we get the total cost of playing tennis. We compute that with a linear equation to describe the relationship between total cost, y is our total cost, and x is the number of hours that we spend. If we spend 0 hours, we plug in a 0 for x. Notice that the annual membership, that our total cost would be $25, just the annual membership fee. So this would represent the value of y when x is 0. It's our constant. So what's the total cost if we spend 100 hours playing tennis? Then we'd plug in 100 for our X variable. We'd do 5 times 100, 500 plus 25, so our total cost would be $525. It's an example of using a regression equation. So the B stands for the slope of the line. You know, it's the amount of change in Y that corresponds to a 1 unit change in X. So if we go back here, so for each additional hour of playing, we would expect, we would pay an additional $5. So this is the expected change in Y for every 1 unit change in X. That's how we interpret the slope coefficient. So again, you know, the A in the equation is just the y-intercept or the regression constant. So here's another example. So in a study of the relationship between education and income, a researcher finds that people with only grade school education have an annual income of $12,000, and each additional year adds an additional $5,000 to a person's income. So this would yield the following regression equation. So with only grade school education, you earn $12,000 for each additional year of education. You earn an additional $5,000 on average. So this equation represents annual income where it depends on the years of education. So what's their predicted income for someone with 16 years of education? So we just plug 16 into the equation and we get $92,000. It's the predicted income for someone with 16 years of education. So, you know, the line, you know, this is just an example here of the regression line provides a simplified relationship of the XY relationship. You know, it's what best line can we fit through this scatter plot. You know, where the line crosses the y-axis here would be the regression constant. See, that's the intercept here, where it crosses the y-intercept. And the slope is the amount of rise over run. You know, how much do we decrease? You know, we rise and then we run over. So it's the amount of slope on the line. So how do we get the line? We basically use this method of least squares. He kind of talks about it in the textbook. Some you can go through some of the calculations there. Don't worry, we're not going to calculate the correlation or the regression equation by hand, and we're just going to have SPSS do it for us. But the text does a good job of kind of walking you through those things. You know, the method of least squares tries to minimize the distance between each point in the line. So, you know, the regression line is the line that is the minimal distance between every point in the line. That's what the method of least squares is. So the errors of prediction, you know, the line was really just a simplified relationship between the points. You know, unless each point falls on the line, there's going to be a little bit of error in the prediction. If you look at this, so here is the regression line, you know, describing this relationship between X and Y. You can see the actual points plotted on here. Let's take, for example, the green point here. Its value is 1.3. If we look at the predicted value here, it's around 2. So then the error of prediction then, so we made an error in predicting the green score. If we were to use this regression line, we'd predict they would have a 2. You know, the error we made was around 0.7. And that makes sense. You know, if we look back at this relationship here, we don't expect everyone with 16 years of education, right, to make $92,000. Some people are going to make more. Some people are going to make less. You know, so there's going to be errors in our prediction. So same thing we found before, right? You know, someone with 16 years of education, we predicted their income would be $92,000. if Sally's income is really $95,000, then the error prediction for salary is $3,000. Our prediction was off by $3,000 for Sally. There is an estimate. It's called the standard error of the estimate, which basically tells you the extent to which a predicted score is likely to be in error. It tells you, gives you a way to estimate how much error there is in your prediction. If we look at our example, our income example again, or someone with 16 years of education earns $92,000. Well, we know not everybody will make exactly $90,000. Some will make more, some will make less. The standard error of the estimate tells us how far off our estimate or our predicted value might be. Let's say in this case, the standard error of the estimate is $5,000. So we can use the properties of the normal distribution to kind of get an estimate of, how distributed our, the actual values might be. So we would expect around 68% of people with 16 years of education to have salaries between $87,000 and $97,000. Basically what we did is we added 5,000 to our estimate. We added and subtracted, rather, 5,000 from our estimate. Because remember, around 68% of scores will be within one standard deviation of the mean. If we could expect around 95% of people with 16 years of education to have salaries between $82,000 and $102,000. Because remember, 95% of scores will be within two standard deviations of the mean. So we can use our standard error then as that estimate. That's telling us how far off our scores may be. And if we assume that these scores are normally distributed, we can get estimates of how far. So we'd expect with 16 years of education, around 95% of people should earn within this range according to our regression equation. Here's a formula for computing the standard error. I'm not going to have you do this by hand, but a couple of things to notice. Notice your R squared here. So, as your correlation becomes larger and larger, your standard error tends to be smaller and smaller. So the stronger the relationship between two variables, less error of measurement you're going to have. Same thing as, correlation doesn't imply causation. Regressing X and Y doesn't imply that, changes in X cause the changes in Y that you see. In another module, we're going to discuss a little bit more about establishing causality. Some assumptions to use linear regression. Your outcome variable needs to be measured on an interval ratio scale, and the X and Y variable need to be linearly related. So that was just a quick overview of the PowerPoint for this week. Be sure to check out Canvas for extra, for some extra notes and some extra readings if this information is confusing you some. Don't forget to check out the other correlation coefficients document, the correlation and linear regression example, how to compute a correlation in SPSS. It's pretty easy. We'll walk through it real quick. You basically go to Analyze, Descriptive Statistics, Analyze, that's not right. Analyze Correlate, there you go, bivariate, and then bring over the variables you want to correlate. So we want the correlation between reading scores and writing scores. You just bring them over. SPS will compute the Pearson's correlation, Kendall's tall, and the Spearman correlation. If you want both of them, you just have to check them off, and you can see your correlations then. So the correlation between reading and writing is about 0.6. So, as reading scores increase, writing scores increase, is what this is saying. You'll always see in a correlation matrix, the correlation between any variable in itself is 1. So you'll always see that labeled in there. And then, your Spearman's correlation will be found in this non-parametrics correlations table. You notice that it's about the same here too. It's got a correlation of 0.6 again. So as reading scores increase, writing scores also increase. If you want to get a scatter plot out of SPSS, you go to Graphs, Legacy Dialogs, Scatter Dot. We just want a simple scatter plot. And we bring the variables over. Let's say we want to be able to predict writing scores from reading scores. We put writing scores on our y-axis, reading scores on our x-axis, and click OK. So look, you can kind of see that positive relationship here, As reading scores increase, writing scores tend to increase. If you want to get one way to get the regression line out of the scatter plot is to double click on the scatter plot here. And if you click on this little symbol here, if you highlight or say add fit line at total, we click on it, and you want to check, you want the linear relationship. You can ignore some of these other ones here. So you would typically say apply, but looks like it's already applied it here. And look, it gives us the R² value here. Let's close out of it. So, at the top of the graph, you can get the R². So our knowledge of reading scores explains around 35.6% of the variability in writing scores, is how we would interpret that. Here's our regression equation. So for someone with a reading score of 0, we would predict their writing score to be around 23.96. And then every increase in for every 1 unit increase in writing scores, we'd expect a 0.55 unit increase in writing scores. All right, did I say that right? For every 1 unit increase in reading scores, we would expect a 0.55 unit increase in writing scores. That's how you interpret the slope coefficient there. There's a regression procedure in SPSS. You go to Analyze, Regression, Linear, and then you would put your writing score in your dependent variable, reading score in on your independent variable, and you could click OK. And there, the R here is then just the correlation between the two. There's your R². There's the standard error of the estimate we were talking about before. You can just ignore this table for right now. And here's your regression equation, is right here. So this is your A term, or remember your regression constant is 23.95, and then this term would be your slope, or your B coefficient, because it's the one that corresponds with reading. So this regression coefficient would be 23.95 or 96 plus 0.55x. Well, that's just another way you can do it. I think it's just as easy to get it out of the scatter plot. So like I said, they're right here, on Canvas, and I try to annotate the output so you kind of know what's going on. I'll also show you how to calculate some of the additional correlations in there, like the point Bias-Zero and the phi coefficient, if you ever need to know how to compute those in SPSS. And then here's the handout with getting the regression line in SPSS out of the scatter plot. There's also a video I linked on a YouTube video that also shows how to get the regression line in the scatter plot. Don't forget the quiz for this week and the data analysis assignment. Basically what we're going to have is a little research scenario. You'll enter the data into SPSS. I'll get you to graph the data. I'll get you to compute the Pearson, Spearman, and Kendall correlations. And I want you to make an argument about which one you think is most appropriate based on your knowledge of the readings. And then a similar thing for problem 2. I want you to compute a scatter plot, get the Pearson's correlation, get a regression equation. We want the regression equation to predict the long form test scores from the short form scores. Then compute the coefficient of determination, and we'll talk a little bit about the errors in measurement. And like I said, if you go through the correlation linear regression example, the example problem is very similar to the data analysis. As always, if you have any questions, shoot me an email, stop by my office, come visit. I'm always happy to chat with you. And best of luck. I'll see you at the next module. Thank you.